screen. Hi, everyone. I'm just going to give it a minute, see if anybody else decides to come into the waiting room. Well, I'll admit them, and then we'll start the class. We're going to do 2.3 today, which is our probability function. So we're going to think about some of the stuff that we did yesterday with our sample space. And we're going to build on it to talk about how we can use our sample space and our ideas to calculate probabilities. Okay. All right. So we'll come back to that. Good. And let me move this, just gonna move this over so I can see better. Okay, all right, good. Okay, so this is chapter 2.3. See if I can get that in focus a little bit. Okay, so chapter 2.3, and this is the probability. Okay, give me a second. Okay. All right. I hope you guys have your lecture examples, right? This is the sheet that we're going to be writing our examples on. Just want to do a quick note that the lecture examples for chapter 2.2, I put up on Blackboard. I sent out an announcement about it, but just in case you didn't see it, I put it on Blackboard. There's now in the same folder that has these papers here, the blank ones, I created a subfolder that has the solutions on it. So each day I'll scan in the solutions that we've actually worked through for the class, and I'll put those up on that place there too. Also, I created another folder for our lecture videos. Okay, that's on our main course material webpage. So you can check there every day too, so that you can try to find the videos that we've done. And I'll see if I can't remember to label it like lecture 1, lecture 2. But if not, it'll definitely be labeled by like the chapter that we're covering. Okay, so keep track of that. If you can't get access to it, send me an email and I'll see what's going on. There may be some, glitch or problem. Also, just a quick thing, I was looking at the syllabus too, and I think in terms of time frame on stuff, we'll see how things go this week. We may get a chance to start chapter 2.6 on Thursday. We may not. If we don't get a chance to start 2.6 on Thursday, then we'll just bump it out into next week on Monday. Also keep in mind that we'll have a quiz this week too, but the quiz will start because this is like online, and I'm gonna start it becoming available like Thursday afternoon. So I'll make it start after our office hours on Thursday. So if you guys have questions on Thursday, like about all the homework, because the homework will be due Thursday night. Okay, so I'll still have office hours on Thursday afternoon. You can come in and ask a lot of questions about stuff like homeworks. How do you prepare for the quiz? And then we'll have the quiz. I'll set that going. The quiz will be, this is what I did in the spring semester. It'll be a 24-hour window, okay? So basically it'll be available for 24 hours. So I'll start it like Thursday afternoon to Friday afternoon, and then that'll accommodate all like different time zones that people are working with, but it'll be set on a timer so that when you start it, you'll have, 45 minutes, say for example, to actually take the quiz. And when we get to like Thursday's class, as we go along, I'll start putting up announcements about like the protocol for taking the quiz and what we're supposed to do, because now it's online and we have to kind of adapt. Okay, all right, so let's go ahead and get started with chapter 2.3, so the probability function. So we talked yesterday about sample spaces, right? We talked about like an event happening. So we have sample spaces, this overall, possibility, total outcome of things that could happen. And then an event is something that we've defined as something specific, okay, within that sample space. Okay, so we're going to use that concept to create the idea, to calculate the idea of the probability. Okay, so let's talk about, if we have something like, we're going to first talk about equally likely events. Okay, as we go along, we'll talk about things that then have weights and stuff. But for now, we're going to talk about equally likely events. Okay, so in terms of equally likely events, we've got the probability, we've got some event E, probability of some event E, we'll call it E, okay? That probability is going to be equal to, okay, just a second. I should be joining. Okay, good. All right, so we've got the probability of some event E is going to be equal to the total number of outcomes in event B, in event E, okay, divided by our total number of outcomes in our sample space. We do this already with like percentages, right? Probability and percentage are very closely related. Okay, probability is going to be a decimal between 0 and 1. Okay, and then if we want to talk about percent, like there's a 24% chance of something happening. That's really a probability. All we've done is taken our probability and multiplied it by 100 to get percent. Okay, so it's the number of outcomes in our specific event divided by the total number of outcomes in our sample space. Okay, so we can write it like this: probability of E. So probability of E is going to be the number of outcomes in event E, so N is for our number, and the number of outcomes in our sample space. Okay, it's just some kind of a nomenclature, but really we're just kind of trying to calculate, sorry, I'm trying to move this around so I can see things. We're trying to calculate things. Okay, all right, so let's talk about some properties of probabilities, okay? And then we're going to start building on that to talk about examples and how we work through and think about different things, okay? So this is like our very first step in thinking about calculating probability functions. Okay, so our first thing is that the probability of any event, let me get this in the light here, probability of any event E is a number between 0 and 1 inclusive. Okay, and we're going to write it like this, right? Our probability of any event E is between 0 and 1 inclusive. Okay, it's really important. I mean, think about it in terms of percents. Like I can't have more than 100% of something. Okay, I mean, we talk about more than 100% in terms of growth and stuff like that, but in terms of probabilities, right, we're just talking about 0 to 1. Okay, 0 to 100% of something happening. All right, so now also second property, the sum of all the probabilities in a sample space must be equal to 1. Okay, so that's like saying I have a sample space. It has all these different events in it, including nothing happening, right? And null set is one of our events too. If I sum up all the probabilities of all those events, it has to be equal to 1. So we're saying basically that the probability of our sample space is equal to 1. Okay, that's important. Now, I just want to clarify, this is the probability of our sample space. This is the number of outcomes in our sample space. Okay, those are two different numbers. Okay, this is an actual number, right? And this is a probability. Okay, within our sample space, we have a probability of 100% chance of something happening. That something could also be nothing happening. Okay, so let's keep that in mind. Probability of our sample space is equal to 1. All the probabilities within that have to sum up to 1. Okay, so third property. Trying different pens here, see which one's not going to die on me. If an event E cannot occur, its probability is equal to 0. Okay, It can't happen. It's possible that I can have a sample space of things. We're going to do examples like this today. It's possible that I can have a sample space of things, right? And then what's going to happen is I've defined an event that's just not possible given the sample space that we have. We'll see in examples what I mean by this. But it's possible that if an event can't occur for whatever physical reason, our probability for that is going to be equal to 0. Conversely, if an event is certain to happen, I've defined the event in such a way that it's a guarantee. If an event is certain to happen, the probability is equal to 1. We'll do also an example like that today so that you can get a feeling for what that looks like. Give me just a second. Okay. Sorry. I don't know why this is getting big. Okay, sorry, I'm having problems with the Zoom here. Try to make it, the window's not getting in the way. Okay. So the way to think about a probability function itself, so we think about P, right? I say P of S. So probability P is a probability function okay, which is a mapping from an event to a number. So we're going to do examples today. I'm going to pull a deck out of a card. I have certain events that are being defined for that. I need to have some kind of a mapping that says, you know, I've got this event that's happening. The probability of an ace of spades coming out of my deck of cards, okay? That's the event, right? And the probability function is the number that's associated with that particular event, okay? So that's how you want to think about what the probability is. It's a way to map it. So we can think about probability of E, where E is some kind of event. So that should be a P. It's not working very well. Okay. So let's think about now, we talked yesterday about complementary events. So let's think about what does that mean if we have complementary events, okay? So if I've got my overall sample space, remember the Venn diagrams that we did before. Here's my event A, right? So A is our event. We've defined A, right? We want to know, you know, we've got some sample space right here, okay? A is something that we're going to be defining. I want to pull this type of card out of the deck, okay? A with a C superscript is the complement of A, okay? So A complement is all the stuff, you know, outside. Let me just shake it in. Yeah. So A complement is everything outside of A, right? Okay, so we want to be able to think about that. Now think for just a minute. We just said before, our whole sample space, our probability of our sample space is equal to 1, okay? If the probability of the whole sample space is equal to 1, and I want to calculate the probability of the complement happening, right? What I'm going to do is I'm going to say my whole sample space minus the probability of A, okay? I can manipulate things like that. We're actually going to do a lot of equations like that where we're manipulating the different probabilities. We're going to talk about how we can actually do that, okay? What are the different kinds of equations that we want to put together and how we think about things. As you're learning this, okay, I find drawing Venn diagrams very helpful, okay? It helps me visualize like how we need to think about, you know, the sample space and the events, especially when I've got like multiple events that are happening and they overlap each other or they don't overlap each other. What does that mean in terms of what I'm trying to do, okay? So keep that in mind. It may help to have some kind of a visual so that you can start to formulate what the math is going to be. Sometimes if you jump right into the math, it can get a little bit confusing, especially when you're first learning it. All right, so example 1, I'm going to pull out my example pages. So example 1 says, we want to find the probability, let's see if I can get this in focus. We want to find the probability of getting a black 6 when one card is drawn from a deck of cards. Okay, now we talked yesterday about our deck of cards. So we have 52 cards in a deck. Okay, the cards are made up of different suits, right? We've got the hearts, the clubs, the diamonds, and the spades. Okay, there are 13 cards in each suit, just as a reminder for what we're doing. Okay, So what I want to think about, I'm just going to start enumerating what things are before I jump right into the probabilities. Okay, so a black 6, those are two things that are happening. This is a compound event. We talked about that yesterday, right? So black is going to identify a particular suit, right? So there are two suits that are black. Those suits are clubs and spades, okay? Now a 6, right? A 6 card, I have one 6 card in each suit. I've got a 6 of hearts, a 6 of diamonds, a 6 of clubs, and a 6 of spades. Okay, so I've got one in each suit, right? So that means, right, if I think about, I've got 4 suits total, but only 2 of those suits are black, okay? And I've got one suit, so there's like 4 total 6 cards, but only 2 of those cards are sitting in the black suit, right? So now that means that I have only 2 cards in the entire deck that will fit this description. The description for this event. The event is the probability of getting a black 6, right? The event is getting a black 6 out of a deck of cards. Okay, so since I have 52 cards total, and I have only 2 cards that are going to fit that event, then my probability, I'm going to write it like this, of a black 6 is going to equal to 2 over 52. Now we can leave it as a fraction. I'm going to actually convert it to a decimal, 0.038. Okay, it's not an exact decimal, which is why I have the squiggly equal signs there. Okay, all right, so we're working it through. We're thinking about it. As we're going along, some of these examples are simple enough that I can actually enumerate like what things are. So I can enumerate how many cards they're going to be. In example 2, we're going to do in just a second. A family has 3 children. You know, they want to know a boy or a girl, so it's a binary choice. So we're going to enumerate these things out, and then we can calculate things from our enumeration. As we go along in the class, we're going to have to start thinking about coming up with formulas or using equations to describe the probability. But for now, at least especially in chapter 2, things are, we can enumerate them as we go. Okay, so example 2 says a family has 3 children. We want to find the probability that exactly 2 of the 3 children are boys. Okay, so this is kind of like that coin toss, right? So because it's a binary choice between boy and girl, right? A coin toss was head or tail. Able to enumerate kids, you know, what are the different possibilities? Hang on. Okay, so here I'm just going to enumerate first all of our different possibilities. Okay, so when I do that, I'm going to get my first child. First, I'm going to start off with, I've got a girl. Okay, so then my second child could be a boy, or it could be a girl. And then my third child could be a boy or a girl, or if it's here, I could have a boy or a girl. Okay, that's if my first child's a girl. This is like our coin toss, right? So we'll do another one where I've got a boy as the first child, and I'm going to repeat what this tree looks like here. So I've got a boy or a girl on the second child, or a boy or a girl on the third child, or a boy or a girl on the third child. Okay, so we've kind of started off here, and it kind of goes like that. So now I'm just going to enumerate what my possibilities are by reading the path line. Okay, so I'm going to write out my total sample space because I can. It's finite and it's straight enough, and it's going to help me kind of think about, you know, what are my possibilities. Okay, so my sample space says the first one goes girl, boy, boy, girl, boy, boy, girl, boy, girl, 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 boy, girl, girl, girl. Okay, see how we're reading the path. Now I'm going to do this again. Boy, 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 girl, boy, girl, boy, and then boy, girl, girl. Okay, so this is our sample space. Let's just count up 1, 2, 3, 4, 5, 6, 7, 8. We've got 8 possible. 8 possible. When we get to chapter 2.6, which is our combinatorics chapter, some of you may have had combinatorics in other classes, some of you may not. We're going to actually talk about, so we don't have to enumerate everything out, you know, what are some of the rules for combinatorics, so I don't have to enumerate everything, and then how do we think about these different combinations. But for now, we can enumerate stuff and then just kind of read our sample space. So we've got our total number of events in our sample space is 8. So we already know that's going to be our denominator, right? Because that's total number of events in our sample space. And we want to find the probability that exactly 2 of the 3 children are boys. So I'm going to enumerate where the combinations I see that have 2 of the 3. So 2 of 3 are boys. And this is our event here. So I've got 2 of 3. So girl, boy, boy is our first one. That one doesn't satisfy. That one doesn't. That's 3 boys. This is 2 boys right here. Boy, boy, girl. Boy,
Does
girl,
it
boy.
matter if there are repetitives or no?
So in this case, order matters, right? Because I have a first child, a second child, and a third child, right? And so order matters. And so even though you're right, I see I've got 2 boys, 2 boys, 2 boys, 2 boys in these cases here. So in this case, in terms of the overall pattern, I have 2 boys and 1 girl, right? So that's one thing. That's like it's one condition. But because we're in a case where order does matter, right? Because we have a first child, second child, and a third child. So then these are actually distinct events. These are different outcomes as part of our event.
But it does but it doesn't say that the first 2 children have to be boys. So does it?
Right, exactly. Now that would be a different event, right? So if
Oh,
they
okay.
said that the first two children had to be boys, then I'd be looking at this one only, right?
Mhm.
Or I guess that would be the only case that would satisfy this one, or this one. I could have 2 cases, right? I could have 3 boys, or I could have 2 boys and then a girl. That would be the case that would satisfy the event that you were talking about. Because we're in a case where order matters, and we have to define the event specifically. Like if we said, I don't even know, if I want like the first child and the third child to be a girl, so I'd have to be able to define, the event specifically so that I know what I'm looking for in my sample space. Does that make
Okay.
sense?
I guess I just didn't expect it. I guess I just didn't expect order to matter.
Yeah, in this particular case, it does, because they're having 3 children and it's in an order. Some of the examples that we're going to do, we're going to say things like, I'm taking something out of a bucket, and then I'm going to take that thing and I'm going to put it in here. So you can see how order is going to matter, because first I have to do this, and depending on the value that I get, maybe I'm going to do this or I'm going to do that.
Mm-hmm.
So the order is going to matter. Or we can just say, I've taken 3 things out, order doesn't matter, and then I'm going to do stuff with them. So we're going to be able to specify, and there are going to be different rules whether order matters or not. It also comes into play when we talk about things like replacement, right? So if I take things out and I put them back, then I've got different rules depending on whether I'm replacing, whether I count order, those kinds of things. These are great questions, and they are things that we're going to get to as we go in class. All I can say right now is make sure that you're reading the question carefully, and you're reading the event carefully, right? Because this one says just that exactly 2 of the 3 kids, not at least 2, right? Because if they said at least
Mm-hmm.
2, then I could have 3 boys, or if order mattered, the first child had to be a boy, that kind of thing. So those are different events. So we just have to define them separately. Okay?
Okay.
Great. So let's talk about our probabilities. So we have our overall sample space. We've got 8. I've got 1, 2, 3 events that satisfy my condition of 2 of the 3 are boys. So there are 3 total, which means I can set up my probability. So the probability that 2 of the 3 are boys is equal to my event outcome over my total sample space outcome, 3 out of 8. And I'm just going to leave it as a fraction, and I'll put a little box around it. Okay? All right. So example 3, where there's a lot of examples in this chapter because we want to be able to see, oh, this stuff actually works when we're doing it out. It really helps. Hope that's in focus for you. Okay, so we're going to draw a card from a deck of cards, and then we're going to find the probabilities of the following events, right? And so what we're going to do is I need to be able to think about different types of things. So the first part is when I take a card out of the deck, I want to find out what's the probability of getting a heart out of that deck. So I need to think about first, how many cards do I have that satisfy that? So I have 13 hearts in a deck, and there are 52 cards. Okay, so that means that a probability of a heart being drawn is going to be simply 13 out of 52, which is equal to 0.25. Okay, that's an exact fraction, so I don't have to do the approximation on that one. All right, let's do this. The probability that I'm going to get a black card when I draw it out of the deck, so I have to think about how many black cards I have. So I've got the black, remember we said was a suit. and sign again. It's a suit, right? And there are 2 suits that are black. Okay, and there are 13 cards in each suit. Okay, so I'm just kind of thinking it through, right? I'm kind of counting it up in my mind, right? I've got 2 suits that are black. I've got 13 cards in each suit. And then that means that for a black card, I have 2 times 13. So I've got 26 cards total that can satisfy it being a black card out of 52 total, which means I've got a 50% chance or probability of 0.5 of actually picking a black card out of a deck. An ace of diamonds now is a very specific card, right? An ace of diamonds, there's only 1 card in the whole deck that's like that. Like this. Okay, so there's only 1 card out of 52. So I've got 1 out of 52 as my probability. Let me write this down here. Is our probability of getting an ace, an 8 of diamonds. Okay, 1 out of 52, if I make it into a fraction, is equal to 0.019. I mean, sorry, into a decimal. Okay. Now, if I want to pull a queen, okay, if I want to pull a queen out, so I have to think about how many queen cards I have. So queen, I've got 1 queen in every suit, right? So 1 queen in each suit. And there are 4 suits in a deck. So I have 4 cards total. So the probability of a queen is equal to 4 out of 52. We have 4 cards total in a deck out of 52 total, and that's equal to approximately 0.077. Okay, a face card. So a face card, when we think about a face card, I'm thinking about a jack, a queen, or a king. Okay, so I've got 3 cards that I'm looking at. Okay, 3 cards, but I have 4 suits that I need to think about in 4 different suits, which leads me to 12 total cards. Okay, 12 total cards that are going to satisfy that event. So that means my probability of a face card is going to equal to 12 out of 52, which is approximately equal to 0.231. Okay, so we're enumerating our event, the number of outcomes that satisfy the event that we've defined out of our total sample space. Okay, we do a lot with cards. We do a lot with picking chips out of buckets. We do a lot with coin tosses. They lend themselves well to probability questions. Okay, so question number 4, example number 4, sorry, is, if I get this into it. When a single die is rolled, now remember we said we're going to assume that all these dies are 6-sided. Okay, when a single die is rolled, find the probability of getting a 9. Well, if it's a 6-sided die, my sides are 1, 2, 3, 4, 5, 6, right? So let's write this down just to be sure. Our sample space, and a 6-sided die is 1, 2, 3, 4, 5, and 6. Right? This is the case where I said you can actually get a null set depending on the event that you've defined. So the probability of getting a 9 is going to equal to 0, right, out of 6, which is equal to 0. Okay, so I'm saying 0 out of 6 because the probability of getting a 9 is 0, and I have 6 total. Like I have 0 9s in my sample space that are going to satisfy this event, right? And then I've got 6 total in my sample space. So really, the probability of getting a 9 is a 0 because there's no way I can get a 9 when all of my possibilities are 1 through 6. Okay, so question 5 is the reverse of this one. When a single die is rolled, find the probability of getting a number that's less than 7. Well, again, I'm looking at my sample space. It goes 1 through 6, right? So that means that all these numbers are less than 7. So that means that since all the numbers in the sample space are less than 7, right? That means that the probability of getting a number that's less than 7 is going to equal to 1. It's guaranteed, right? Because all the numbers are less than 7. Okay. All right. So let's talk about complementary events, right? So this is a complementary event. This is example 6 I'm looking at. Okay. So it often happens when you get something like this. We'll read it and then we'll deconstruct this question here. So example 6 says, in a study, it was found that 24% of people who were victims of a violent crime were aged 20 to 24 years old. If a person is selected at random from this pool of victims now, okay, if a person is selected at random, find the probability that that person is younger than 20 or older than 24. Okay, it doesn't really, this question's worded a little bit funny. Like I added it in there that we're still looking at just this victim pool, okay? So we're not looking at like the overall population. We're gonna get to questions like that much later on in the semester. But right now we're just looking at this victim pool. Okay, so within this victim pool, right, 24% of them are between the ages of 20 and 24. We wanna find out what's going on, what percentage is it, you know, what's the probability of somebody being younger than 20 and somebody being older than 24, okay? So that's what we're gonna look at. So I'm gonna write it down, start writing, you know, basically I'm gonna take the percent. Okay, the percent's going to give me a clue about my probability, right? Remember I said there was a relationship between percent and probability? Okay, so I'm going to say that the probability that the victim is between 20 and 24 years old is equal to 0.24. Okay, I got that exactly from my probability, right? So I'm from my percent, 24% divided by 100, that's how I got my probability, 0.24. Okay, so now that means the probability that the victim is not aged between 20 and 24, okay, that's going to be my whole sample space minus this chunk right here. So my whole sample space, remember, has a probability of 1 minus 0.24, okay, which is going to give us the probability of 0.76, okay. So that means we have a 76% chance of victim being younger than 20 or older than 24 years, okay? If we want to say just those who are younger, right, we're going to need more information. We're actually going to talk about this stuff in statistics, okay? We need actually more pieces of information so that we can get a feeling for, you know, how things are being laid out within our probability scheme. But for now, we're just doing a complementary event, okay? I have the probability of somebody being this age, and I want to find out the probability of somebody not being that age. All I did was subtract it from 1 because 1 is the probability of my sample space. Okay. So let's talk about some properties again of our probabilities, okay? So we talked before about mutual exclusion, right? Yesterday we talked about that. Remember, mutual exclusion was where I had my whole sample space and I had event A and event B, okay? And their intersection was the null set. They have nothing overlapping, okay? So let's just think about that. So we've got A and B are two events in our sample space and they're mutually exclusive. Okay, so it's going to look like, remember our sample space like this. Here's A, here's B. Okay, in terms of they don't overlap at all. Okay, so what I'm going to write is the probability of A union B is equal to the probability of A plus the probability of B. And that's if they're mutually exclusive. Okay, there's no overlap between them, right? So the probability of the union of these two, which is, you know, both of those things happening, is the probability of A plus the probability of B. Okay, they're not overlapping, so I don't have to worry about anything interfering. That's property 1. Property 2 says, I'm going to write it in words and then we'll put it in math notation just so we can see it both ways. Okay, so if there are an infinite number of events, and I'll call them, let's see if I can get this straight here, A sub I, right, where basically I goes from 0 to infinity, right? I've got all these different events and I can have an infinite number of events within a particular sample space. And they are all mutually exclusive. Okay, so I've got this big sample space and I have potentially an infinite number of events, but they don't overlap each other. Okay, so the what this means is, I was just going to say it, but let me write it up. Then the probability of their union is the sum of their individual probabilities. Okay, all we've done is taken property 1, which says I've got 2, right? The probability of their union is the sum of their individual probabilities. And I've extended it to say this thing's going to scale to an infinite number of events that are all mutually exclusive. Okay, so let's write it out in math, right? So the way I'm going to write it, not going to write probability of infinite numbers, but I'm going to say the probability, okay, of the union. I've got I equals 1 to infinity. This basically says I've got the union of all of these. So this is like probability of A1 union, A2 union, A3, so on and so forth up to infinity. Okay, this is how we're going to write that notation. It's going to equal to the sum from I equals 1 to infinity of their individual probabilities. Okay, so all I did was write it in words first, and then we wrote it in math, just so we can get accustomed to seeing how things look in math. And we're going to stipulate too, we'll say that this only works if each of these is equal to the null set. Okay, so this is our definition for mutual exclusion, right? That each individual, right, A sub I intersection with A sub 2 is the null set, A sub 1 intersection with A sub 3 is the null set, and so on and so forth. So we're just basically saying these things don't overlap at all. Okay, so property 1, okay, extends out to an infinite number. Question 2, the probability of the null set is equal to 0. And the reason this is true, we can see mathematically, is like this. I can say the null set is the complement of my sample space, okay? And I know that means that the probability of the null set is equal to, let's see, the probability of the complement of my sample space, okay? Now, this right here, right? Remember, our probability of our sample space, we've said before, probability of our sample space is equal to 1, okay? I'm going to have something happening, okay? And what I'm going to do is I'm going to substitute this, right? So the complement of our sample space is equal to 1 minus the probability of our sample space. And because we just said this was equal to 1, this is 1 minus 1, which is equal to 0. I'm just showing you the math on it so that you don't, just kind of take, this is our property here, and this is y. Okay, we're going to try to get into the habit of thinking about manipulating these probabilities. We're going to do a lot of that. Okay, our fourth property, if A is a subset of B, then our probability of A is less than or equal to the probability of B. Okay, and this A is a subset of B. We say that A is contained in B. This looks like a C, but it's actually like an elongated C. Okay, right here. All right. Here's a proof for that, which I can write up on the board. It's a few lines using the probabilities, but I want to spend our time. Actually, there's an example that's more important in just a second. So I can put this up later. The reason why that is. Okay, so our fifth property, for any event, call it A, the probability of A is less than or equal to 1. Okay, and this stems right from here. Okay, and basically we're going to say that A is a subset of our sample space, right? So then it has to be less than or equal to the probability of our sample space. Okay, our sixth property is super important. I'll put a bunch of stars on it.
Could you go back 1 sec to property 4?
Maybe to property
5, I mean, sorry.
How's that?
Thank you. Thanks, I'm set.
Sure, no problem. Right. Like in a lecture, right, I would have this up on a board, and then you guys could have time to copy it down, but on a piece of paper, you don't get much time. All right, so this property here is super important. Okay, we're actually going to use this one a lot, so let's do this. So this says the property of A union B is the probability of A union B is equal to the probability of A alone plus the probability of B alone minus the probability of A intersect B. Okay, and I'm going to put a box around it, and we're going to star it multiple times. So let me write out in words like what this actually means too here. So what we're saying here is this is the probability of A alone, probability of B alone, and this is, we have to subtract out the double counting. And let's just draw a picture so that we can see the Venn diagram helps a lot. Okay, so when I think about my Venn diagram, right, I've got my sample space, I've got my probability, here's my A, and then here's my B. Okay. Now what happens is, right, I've got A alone, which is this whole thing right here. Let's do this, maybe I can do it in different colors. So I've got A alone, okay, and I've got B alone. Put that one in green, right here. Okay. Now, the probability where they intersect each other, right, is right here. Okay. So now what happens is, if I just count A alone and I add B alone, I'm going to have like about a bunch of double counting that's happening because they're overlapping in that spot. So I need to subtract out that double counting because I'm going to get it here. Okay. So that's what this is right there. Okay. So this is a really important thing here. I just want to work through the reason why and some of the proof on this because it's important so that you know how you can start manipulating and how you can start thinking about how these probabilities hold together. So let's actually write this out. So this is going to be, I'll write this as, okay, so this is probability of A intersect B, and I'll write this as probability of B here. Okay. So let's write down what each of these things are. So I'm going to say my probability of A is equal to the probability that A intersect with B complement plus the probability of A intersect B. So let's think about, I'm just going to talk it through, right? So A intersection with B complement. So B complement is everything outside, including our whole sample space and including this bit of A, right? This part here, A intersect B, that's, I'm going to add back in. So my A is all of this stuff. Okay, that's, I'm adding all this stuff in. We're going to do the same thing for B. So then this is going to be the probability of B intersect A complement plus the probability of B intersect A. Incidentally, these two here are the same thing. Even though they're written in a different order, A intersect B, B intersect A, that's the same thing. Okay, we're going to exploit that later when we talk about stuff. So let's add things up. So if I say the probability of A plus the probability of B, I'm going to use these definitions here in my answer. So I'm going to go the probability of A intersect B complement plus the probability of A intersect B plus, this is A now, right? Plus this is B, B intersect A complement, plus I'm going to write it to look like this so that you can see how we're going to add it together. Okay, so all I did was take these definitions here and I plugged them in for A plus B. Okay, now what I'm going to do is I'm going to combine them. Okay, so this is going to equal to probability of A intersect B complement plus the probability of B intersect A complement plus the probability of A intersect B. That's one of them. I'm going to add in separately probability of A intersect B. The reason is, what I'm going to do is I'm going to take this part here and I'm going to subtract it from both sides of the equation. This is A plus B. Okay. I'm going to subtract this part here, probability of A intersect B, right? So now I'm going to get the probability of A plus the probability of B minus the probability of A intersect B is going to equal this bit right here. So let's add that in. Probability of A intersect B complement plus the probability of B intersect A complement plus the probability of A intersect B. Okay, so I did. So all I did was move this over to that side. Okay, so let's just draw a picture of what we're looking at here. Okay, so you can kind of see like what I'm trying to do here. So the probability of A intersect B complement is going to look like this. So here's our sample space, right? And then I've got A and then B. Okay, A intersect B complement is just this bit right here. So it's just A alone without any of the part that overlaps with B. Okay, the probability of B intersect A complement. I'm going to draw our sample space. Here's A. Here's B. Okay, that's this bit right here. Okay, so it's just B alone. Now A intersect B. I'm going to draw our sample space. So here's our A. Here's our B, and that's this bit right here. Okay, so when I put all these three things together, right, what am I going to get is, let's draw it out so then you can see. Here's A, here's B. So I'm going to shade in the bits as we go. So here's A alone, here's B alone, and then here's their intersection. Oops, sorry, you can see that. Here's their intersection. So this, we actually talked about, we drew a Venn diagram for this yesterday, and this is the probability of A union B. Okay, so what we did was we proved, okay, by manipulating the different probabilities that the probability of A plus the probability of B minus the probability of A intersect B is equal to the probability of A union B. Super important. You're going to use this one a lot. Okay, so it's a really important piece of property, how probabilities are going to combine. But it helps to think about your Venn diagrams. Okay, it helps to think about, to know that you can actually combine probabilities in this way. Okay, all right, I'll leave this here for just a second if you want to finish copying it down, and then we're going to start on example 7. We're just going to start manipulating, using this equation to manipulate probabilities. Okay. All right. Okay, so example 7. Oh, looks like my the thing didn't come right. So this should be a union. Sorry, it's sometimes these things don't resolve really well. So this is a union on part B. So this is probability of A complement union B complement. All right. So so we've got, and then this should be this is A union B right there. All right. I don't know why sometimes Microsoft Word does weird things. All right, so example 7 says, let A and B be two events defined on our sample space S. The probabilities of each event are probability of A alone, 0.3, which is the total circle of A, probability of B, which is 0.5, and the probability of A union B, which you can't see on your page, A union B, is equal to 0.7. Okay, so we want to find a bunch of things. The first thing is we want to find the intersection. That's part A. Intersection of A and B. Part B says we want to find the union of A complement and B complement. And part C is we want to find the intersection of A complement and B complement. Okay, so let's start working through piece by piece. So A says we want to find probability of A intersect B. Okay, so I'm going to use the equation that we were just talking about, right? And this equation says probability of A intersect B is the probability of A plus the probability of B minus the probability of A intersect B. Oops, sorry, this is equal to, let me make this as a dot, and this is equal to probability of A union B. Okay, so we're going to use this equation here, okay, to help us find the intersection. All right, so let's plug things in because we were given all these individual pieces, right? I've got the A, I've got the B, and I was given the union. So I'm just going to plug them in and I'm going to solve for my unknown. So it's going to look like 0.7, which is my union, my probability of A, 0.3, plus my probability of B, 0.5, minus the probability of A intersect B. Okay, I'm going to add these up, subtract them from that side. Right, so I'm going to get minus 0.1 is equal to minus the probability of A intersect B. Oops. So we can say the probability of A intersect B is equal to 0.1. Okay, all I did was plug it into the equation and I worked it through. I need to do that one first, right? Because this, having the intersection, is going to help me find the other questions that are being asked. On something like a quiz or a test, right, I'm just going to give you these things, right? And then I'm just going to ask you for stuff, and you're not going to know, like necessarily, like I may not ask you for A, right? You'll just have to know that you can calculate A, right, which is the intersection of A and B, and then use it to help you calculate other things. Okay, so keep this in mind. This is a really important formula. All right, so that's part A. Part B says I want to find the probability of A complement union B complement. Okay, well, first I need to visualize what is it that's being asked here, A complement union B complement. So I'm going to draw out my sample space. Okay, so I've got A, and here's B. Okay, so let's draw it out with different colors again. So, and then I'll write A complement. So my A complement is everything outside of A, including parts of B that don't overlap with A. So A complement. And then B complement is everything outside of B, including A. Okay, so the only thing that's left unshaded, okay, which maybe you can't see very well on the screen here, only thing that's left unshaded is the bit where they overlap. Okay, so where they intersect each other. Okay, so keep that in mind. So this A complement union B complement is going to be the complement of the intersection. Okay, the drawing helped me visualize that. Maybe I would have had a harder time thinking about that if I hadn't actually done the Venn diagram. So the Venn diagrams can help you. Okay, remember the probability of our sample space is equal to 1, so keep that in mind. So I'm going to say the probability of A complement union B complement is equal to 1 minus the probability of A intersect B. Okay, because I want to take out this little bit here from the whole sample space, and that's going to give me what's all left over. This is 1 minus 0.1, which is equal to 0.9. Okay. And part C, I'm going to use I have a blank page on the back. So part C, so part C on this question says, I want to find the probability of A complement intersect B. Okay, so I'm going to draw another picture so I can visualize like what that's talking about here. So.
Could you go back for 1 sec?
Yeah, yeah, you bet. You want to see part B? Let me know when you're ready.
All set.
Okay. I will post these two later today so you can check to make sure that you wrote everything down correctly. Right, so part C I need extra space for because I write really big. So part C, I've got the probability of A complement B. So let's think about that for a minute. So I've got my whole sample space, right? And I've got A, and I have B, okay? So let's think about what things are. So A complement, right? So A complement is everything outside of A. But it's also everything outside of B. I mean, outside of A, which includes parts of B. All right, now we want to find, this is intersection with B. So then where does this A complement? Now you notice this little bit, this little sliver, right? The intersection of the two is not included in this A complement. So this B, intersection with B, means I'm going to outline my B here. So this is my B, right? This is the part that I outlined in darker part. I'll just draw it off to the side here too. Looks like this. Okay. This part right here is where our complement overlaps with our B event. Okay, so that's what we're looking for, the probability of A complement B. Okay, so I want to be able to do that. So where does this happen, right? When I think about this, A complement intersect B is going to equal to the probability of B minus the probability of A intersect B, right? So B is the whole circle, B is like this whole thing, right? And then I want to take out that little sliver that those two have in common, which is this intersection part, right? And then that's going to give me this probability right here. So I'm going to add these things in, give from what I've calculated and what I was given. to get 0.4 as my probability. Okay, the Venn diagrams, the pictures are going to help you be able to do.
On our page, it says A complement intersection with B complement.
Oh, oops. Yeah, so let's, what I do with that? I think I didn't want to do that one, but I think we're going to cover that one. We did the union of that one. So that's a typo. It should be A complement intersection of B, which is what I wanted to actually show you. A complement intersection of B complement. We can do that at some other time too. I think we actually did some of those in a different example. We did, yeah, we did the union. So don't sweat it. This one, this is a typo. This should be on part here. This should be just A complement intersection with B. Sorry about that. We'll do the complementary parts later. Other things. Okay. So example 8. Let's see if I can get this in the page here. There, example 8, good. So example 8 says the probability that A intersect B is greater than 1 minus the probability of A complement minus the probability of B complement. Okay, so what I'm trying to do here, right, I'm just trying to show this, right? It's sort of like a proof-ish. Okay, so we're just going to be working through kind of a logic function on here. So let's just draw pictures so we can visualize what's happening. So I've got my sample space, and I've got A, and I've got B, okay? And then this bit right here is our A intersect B, okay? So that's the thing that we're trying to look for, that A intersect B is 1 minus the probability of A complement minus the probability of B complement. Okay, so remember that our probability of our sample space is equal to 1, okay? So now I get some pieces cut before. So what we've got is probability of A intersect B is equal to the probability of A plus the probability of B minus the probability of A union B. All I did was take that equation that we used before and I manipulated it. So now I have the intersection and the union on opposite sides right there. All we did was move it around. And then let's remember our probability of A is equal to our sample space probability 1 minus the probability of A complement. Probability of B is equal to 1 minus the probability of B complement, same idea, okay, that we did for A. Now I'm going to put them together. I'm going to say the probability of A union B is less than or equal to 1, okay? And the reason that this is because the probability of A union B is equal to probability of A plus probability of B minus the probability of A intersect B, okay? So we're using that, right, to help us with this. So that's like saying basically, you know, it's possible that A and B could take up our whole sample space, okay? But we know that the maximum that it could possibly be is 1. So it has to be less than or equal to 1, okay? Because our probability of our sample space is equal to 1. And this, the union, remember our union, A and B, looks like all of these things, including what they have overlapped, okay? So probability of A intersect B is going to equal to, I'm going to put these together, 1 minus the probability of A complement plus 1 minus the probability of B complement minus the probability of A union B. Now we just said that the probability of A union B has to be less than or equal to 1. I'm going for max here because we're talking about greater than or equal to. So I'm going to substitute this value for 1, okay? And then I'm going to start opening up these parentheses and combine. So 1 minus A complement plus 1 minus C complement minus 1. Okay, so I've got 1 plus 1 minus 1. It's going to give me 1 minus the probability of A complement, oops, plus the probability of B complement. This should be minus the probability. And that was what we were asked to show. The reason I'm going through these problems here is so that you get a feeling for how you can manipulate the probabilities and how they can be worked around. Okay, it'll help you when you're thinking about homeworks, when you're thinking about the quizzes, how you're going to make these things work. Okay, give you guys a second to finish writing that down, and then we'll go on to example 9. There's a lot of examples in this, but it's good because you want to be able to think through. So example 9, and remember I'm going to post the solutions for this too, so in case you missed it, you'll be able to check it. So example 9 says, we're going to draw a single card randomly from a deck of cards. We want to find the probability that it is either a 9 or a diamond, okay? So let's think about it. So I'm looking at the probability that it's a 9 or a diamond. I'm going to call D for diamond, okay? So our union says it could be either or, okay? So, which means I have a probability of a 9 plus the probability of a diamond minus the probability that I'm going to get the 9 of diamonds, okay? Because remember, there is an overlap between these two here. So let's think about it. So what we're doing here is, right, here's my sample space. That's my whole deck of cards. This is the probability that I get a 9. This is the probability that I get a diamond, okay? This is what I'm looking for here. Then I'm just going to count them up. So I got to think about the number of 9s in a deck. I've got 1 in each suit. I have 4 suits. I have 4 9s total. And I have the number of diamonds in a deck. It's a whole suit, so there are 13 cards total, okay? And the number of cards that are 9 of diamond, I only have 1 card that's like that. Okay, so I've got 4, 13, and 1 out of 52, and we have total sample space 52 cards. Okay, so we're going to use this, right, these fractions to help us come up with this equation right here. So I'm going to start plugging things in. So I'm going to say the probability of a 9 union diamond is going to equal to the probability of getting a 9 is a 4 out of 52, plus the probability of getting a diamond is a 13 out of 52, minus the probability of getting a 9 out of diamonds is a 1 out of 52. I'm going to add them all up, and I'm going to get 16 out of 52, which is approximately equal to 0.308. And when you guys do these, do the decimals, you can go out to 3 places after the decimal point. Okay, you can leave it as a fraction, or you can go out to 3 places depending if you want to know how to round it. Okay. One second. Okay. So now we'll talk about example 10. This one says, in a hospital unit, there are 8 nurses and 5 physicians. We have 7 nurses and 3 physicians are female. If a staff person is selected at random, right, from this pool, we want to find out what's the probability that the person that we're selecting is a nurse or a man. Okay, so let's think about it. So first I'm going to draw out my sample space. And by drawing out, I mean I'm going to make a table so I can sort of enumerate what my possibilities are. Okay, so I've got my staff, and I've got nurses, and I've got physicians, and then I've got the total. I want to think about that. So let's draw this out. I've got female, and male, and total. I probably should have made this table a little smaller. Okay. All right, so let's fill it in. So the number of nurses that we have, female nurses, are 7, and the number of male nurses is 1, and the total number of nurses is 8, right? So it sums up to what they gave us. The number of female physicians are 3, number of male physicians are 2, total number of physicians is 5, total number of women that we have are 10, total number of men that we have is 3, and total number of people on staff is 13, okay? So this is our total line here, you know, total lines, and then these are individual distributions, okay? So what I want to think about is the probability that I get a nurse union with a male is a nurse or a male. Okay, so I'm going to look at the probability of a nurse plus the probability that it's a male minus the probability of a male nurse. Okay, because we actually have a male nurse, so we have to count that in. Okay, so that means I've got 13 total, so I'm going to be taking a look at my different numbers. Okay, so the probability of the nurses, total number of nurses is 8, out of total number of staff is 13. Total number of men is 3, out of the total number of staff is 13. Now, my double counting, my male nurse, he's right here, minus 1 out of 13. Okay, so I just kind of read through my table here. and I'm going to add everything up, and I'm going to get 10 out of 13, which is approximately equal to 0.769. And that's the probability that we're going to get a nurse or a male. Okay? Nurse plus male minus the male nurse, because we don't want to double count. Okay? It helps to enumerate. Okay? Trying to go a little slower. I can't see you to see that you're still writing, so I'm going to try to go a little bit slower and give you a second to finish writing it out, and bear with me if you're sitting there just waiting for me to move on. Okay, so we'll go on to example 11. Example 11. Okay, so here we have, oh, sorry, this is, this should be union. Sorry, that's not coming through. All right, so the probability of A is 0.7, probability of B is 0.4, probability of A complement union B complement is 0.75. We want to know what's the probability of A union B, because we're going to use all the different things that we have to kind of manipulate stuff. These kinds of questions are like common exam or quiz type questions, because we want to see that you can remember what's the important formula, and then how do I manipulate these different probabilities, the A, B, and the complements, and how do they go together, which is why a picture can help you a lot. Okay, so first thing I'm going to do is I'm going to draw out my sample space and my events. So I've got A, and I've got B. All right, so let's think about what we have. So my A complement is everything outside of A, including this bit of B. My B complement is everything outside of B, including parts of A. So the only thing not shaded is equal to A intersect B. It's hard to see on this picture that I drew here, but A intersect B is not shaded. Okay, so let's think about that. So what I'm going to do is I'm going to say A complement union B complement is going to equal to my whole sample space minus my A intersect B, right? So A complement union B complement, right, is this whole sample space, everything, minus that little sliver where they overlap, which is our intersection of A and B, okay? So that means I can say the probability of A complement union B complement is equal to 1 minus the probability of A intersect B. That's going to help me. So now let's plug things in. So probability of A complement union B complement, we were given 0.75. And this is 1 minus probability of A intersect B. So I'm going to subtract 1, divide by -1. So I'm going to get 0.25 is equal to the probability of A intersect B. I'm going to need that to help me solve the other part. Okay, so my union part. Remember our equations, the probability of A union B is equal to probability of A plus the probability of B minus our double counting, A intersect B. Okay, now I was given probability of A, probability of B at the beginning, and I just calculated out the probability of their intersection. So now I can plug things in to find out what their union is. So it's going to be 0.7 plus 0.4 minus 0.25. Okay, and for that, I'm going to get 0.85, which is equal to the probability of A union B. Okay, so drawing a picture is going to help you. It's going to help you visualize what's being asked and where you need to go from that, right? Because you think, I've got A and B, and then, you know, oh, A union, I've got this great formula, but you're missing this intersection part. Okay, so if you're missing the intersection part, that means you have to go solve for that. And how you solve for that is you need to start thinking about how your probabilities relate to your overall sample space, to your complements, what were you given, and that's going to help you. Okay, so pictures are always worth a lot. Okay, I'll give that a second. Okay, so I'm just going to talk about something really quick, and then we'll roll into example 12, which has multiple parts to it that we can actually work our way through. Example 12 is good. I've debated whether to put example 12 into a video and then just let you watch it, but I think we have some time so we can actually work through it. So let's talk about 3 events. We've talked about 2 events, A and B, and we want to be able to talk about 3 events now too. So say I've got a sample space, right? This is my overall sample space, and I've got event A and event B, and I've got event C. Okay, so event A is right here. Now event A is going to overlap with just B right here, right? And it's going to overlap with just C right here. And with this little bit right here, it's going to overlap with A, B, and C. So this here, this little sliver, where I've shaded it in, is the place where A, B, and C all overlap each other, okay? So we want to be able to think about, we've got 3 events that are not mutually exclusive. Remember, mutual exclusion is going to look like I've got a sample space, I've got event A, event B, event C. They don't overlap at all. So these events are not mutually exclusive, okay? All 3 of them overlap, you know, in a particular spot. So we want to take some of the ideas and the properties that we've had before about how we combine probabilities and then use it for when we have now 3 events, okay? So if I've got the probability of A, union B, union C, right? So I've got all 3 of these things happening. That's like this big Mickey Mouse shaped bubble, right, that I'm going to be putting together. So I've got probability of A plus the probability of B plus the probability of C. Now I have to start subtracting the double counting, right? So I've got A, B, and C, and I have to subtract where A and B overlap each other. I have to subtract where A and C overlap each other. And I have to subtract where B and C overlap each other. Remember, these 2 things, they go both ways. So this is equivalent to B intersect A, so I don't have to write them multiple times. But then I have to add back in, because I've just subtracted out all this stuff, which means I've subtracted out this shaded region. So I have to add back in where they all intersect each other. Okay, so I'm adding back in because I've subtracted out the double counting, but I subtracted out too much, so I'm putting it back in. Okay, so we've taken our original idea about 2 events and we've extended it to 3. Okay, and then example 12 is kind of going through a deck of cards, right? And then we're going to be looking at how do we do this in different types of events, do things overlap, and then how do we get these combinations to occur? All right. So example 12 says, let's see, example 12 says, I've got 1 card that I'm drawing from a deck. I've got 52 cards in the deck. I want to know what's the probability of a 7 or an 8 or a 9, okay? Which means that I'm looking at the probability of a 7, union 8, union 9, okay? Now it's not possible for me to have a case where I have a 7 of 8, or if you like Star Trek, a 7 of 9, okay? So it's not possible for me to have that, so I'm not going to be worrying about subtracting out the places where they overlap, because it's not possible for me to have overlap in these cases. 7 or an 8 or a 9 are all mutually exclusive events, which means I've got a probability of 7 plus a probability of 8 plus a probability of 9, okay? That's how I'm adding it up. So a lot of these probabilities, how I'm adding them up and how I'm combining them are also going to relate to the given sample space that we're working with, right? So we had this particular idea that we just talked about, okay, with 3 different things. I need to subtract out their overlaps, and then I have to add back in the big overlap. But if they're all mutually exclusive, like a 7 or an 8 or a 9, okay, this particular event, that means I can ignore all the spots that it's being overlapped, okay, because those probabilities are equal to 0. Okay, so let's write it out. So the number of 7s in a deck of cards is going to be 4. The number of 8s in a deck of cards is 4. And the number of 9s in a deck of cards is 4, right? There's 1 for each suit, and we've got 4 suits total, okay? So that means that the probability of a 7 is going to be 4 out of 52. The probability of an 8 is equal to 4 out of 52. And the probability of a 9 is equal to 4 out of 52. Okay, so I'm just going to be summing these up, right? So the probability of a 7 union 8 union 9 is equal to 4 out of 52 plus 4 out of 52 plus 4 out of 52. Obviously, I could have written 12 out of 52, which is equal to 12 out of 52, which is approximately equal to 0.231. Okay. I had to think through, you know, what do I have in my deck? You know, how many, 7s, 8s, 9s do I have? Do they have overlap? They don't. So I'm just going to add up their individual probabilities to get my answer. Okay. Part B says we want to find the probability of a spade or a queen or a king. Okay. So I can get a queen of spades or a king of spades, but I can't get a king of a queen, or, you know, these two things are, queen and a king are mutually exclusive, but queens and kings both exist within the suit of spades. So we're going to have some overlap that we need to take a look at. So if we think about it, like if my spades, let's draw it like this. Here's my sample space for spades. Here's my sample space for queens. And here's my sample space for kings. Okay, so where they overlap is here, where they overlap is here. Okay, you can see obviously that the king and the queen aren't going to overlap, but they do overlap with the spades. Okay, so when I go to do this, this is going to be the probability of a spade plus the probability of a queen plus the probability of a king minus where they overlap, spade intersect queen, minus the probability of spade intersect king. Okay, so let's fill in the blanks on these things. So we're going to think about how much we have. So the number of spades in the deck of cards is 13, right? It's a whole suit. So we've got 13 cards total that we can work with. The number of queens, we've got 4 queens, right? 1 for each suit. Same thing for kings. 1 for each suit. Okay. So I also have a queen of spades. There's only 1 card like that in the deck. And I've got a king of spades. And there's only 1 card like that in a deck. Okay. So I'm going to add up and subtract out all of these probabilities. So the probability of a spade or a queen or a king, okay, spade, queen, king, is going to equal to, let's add these things up. So 13 out of 52, probability of spades, plus queen, 4 out of 52, plus king, 4 out of 52, minus our first overlap, 1 out of 52, minus our second overlap. Queen of spades, king of spades. Okay, now the individuals here. So I'm going to sum all these up. I got 19 out of 52, which is approximately 0.365. Okay. This example kind of belabors the point, but it does help, I think. All right, so part C says the probability of a club or a face card. Okay, so we're going to think about that. So that's going to be a club or a face card. So I've got the probability of clubs. Clubs is a suit, right? And then face cards, remember that's our jack, queen, and king. So I've got jack, queen, and king in each of our suits. Okay, so it's possible that I'm going to get a club, like a jack of clubs, queen of clubs, king of clubs. So I have to discount that overlap here. Okay, so the number of clubs that we have is 13. This is kind of like the examples that we did before. Face cards is going to be, we've got 4 cards because I've got 1 in each suit times 3 faces, right? So 3 faces times 4 suits is going to give me 12. And the number of face cards of the club suit, clubs, I'm going to write face of clubs. It's jack of clubs, queen of clubs, king of clubs. Okay, for each of those, I've got 1 jack of clubs, 1 queen of clubs, and 1 king of clubs. So I've got 3 cards total. Okay, so those are the things I'm going to put into our equation. So the clubs, so this is 13 out of 52, plus 12 out of 52, minus 3 out of 52. Sorry, that's a 2. Okay, I'm going to add it up. 22 out of 52. Okay, which gives me approximately 0.423. as my probability of a club or a face card. Okay, so part D says, I'll leave maybe if you're still writing that. So part D says we're going to do an ace or a diamond or a heart. So the same type of a thing that we did before. So the probability of this is I've got the probability of an ace plus the probability of a diamond plus the probability of a heart. Now I can get an ace of diamonds and an ace of hearts. So I have to discount those, double counting. Ace of diamonds minus the probability of ace of hearts. Okay. All right, so let's enumerate. So the number of aces is equal to 4. Number of diamonds, it's a whole suit, so there are 13 cards total. Number of hearts, it's a whole suit, so there are 13 cards total. I've got an ace of diamonds, that's 1 card. And I've got an ace of hearts, which is 1 card. Okay, so it's my double counting, I have to take that out. So let's go ahead and plug those in. So probability of aces, so 4 out of 52, plus the probability of diamonds, 13 out of 52, plus the probability of hearts, 13 out of 52, minus the double counting for the ace of diamonds, and minus the double counting for the ace of hearts. So I add it all up, and I get this is equal to 28 out of 52, which is approximately 0.538. Okay, you're tired of cards yet? It's a lot of card problems. They make good, probability functions. All right, part E says, what's the probability of, oops, this shouldn't be, this is a typo. This is a 9, or a 10, or a spade, or a club. Okay, so the probability of a 9 or a 10 or a spade or a club, so let's add it up. So this is the probability of a 9, plus the probability of a 10, plus the probability of a spade, probability of a club. Now I can get a 9 of spades, a 9 of clubs, and a 10 of spades and a 10 of clubs. So I have to double count those. But I don't have any overlap of all 3, okay, or all 4. And I don't have any overlap of the 9 and the 10 or the spade and the clubs. Okay, so I'm going to subtract out probability of the 9 of spades and the 10 of spades. And I'm going to subtract out the 9 of clubs and the 10 of clubs, because we want to get rid of the double counting. Okay, so let's enumerate how many we have off to our side. Number of 9s in our deck is 4. I've got 1 for each suit. Same thing for 10s, which is 4. Spades, that's a whole suit, so there's 13. Clubs, that's a whole suit, so that's 13. 9 of spades, that's 1 card. 10 of spades, that's 1 card. I've got the 9 of clubs, that's 1 card, and the 10 of clubs, that's 1 card. Okay, so I'm going to fill in all the blanks here. We're going to sum everything up and we'll get our probability. Okay, so this is going to be 4 out of 52 plus 4 out of 52 plus 13 out of 52 plus 13 out of 52 minus now our double countings. 1 out of 52 minus 1 out of 52 minus 1 out of 52 minus 1 out of 52. I'm enumerating, I'm like writing them all out so you can see where things are. Okay, but if you're answering this, like you just write minus 4 out of 52 and we'll get it. We'll understand. Okay. This sums up to 30 out of 52, which is approximately equal to 0.577. So that's the probability of a 9 or a 10 or a spade or a club. We're increasing the number of events, right? So it should increase our probability in our sample space. Leave that there for just a second. Okay. Right. All right. So example 13. Let's see today. Example 13 says, we're back to dice. So we've got 2 dice that are rolled. Remember we did that whole enumeration of the big table that gave us, I've got die 1, die 2, I've got different combinations. So I've got 36 possible combinations when I roll. Okay, so let's write that out. So 36 possible outcomes. I'm going to try to avoid actually writing out that table each time, if I can help it, because it takes time to write out. But just remember, we enumerated that in lecture 2.2. So if you can't remember, that was a reference. That whole table was done in chapter 2.2. Okay, so we want to find, we've got 2 dice rolls. We want to look at our outcomes. And the first event that we're defining is that we get out of these 2 dice a sum of 8, a 9, or a 10. Okay, so let's enumerate what our possibilities are. So sum of 8. So I'm going to look at what I could get. So my sample space for this event, sum of 8, is going to be, well, I've got a 2 and a 6. So die 1 is 2, die 2 is 6. Then I sum them up, I get 8. I can also have a 3 and a 5, a 4 and a 4, a 5 and a 3, 6 and a 2, and that's it. Okay, so I've got 1, 2, 3, 4, 5 5 possible outcomes. Okay, when I go up to sum to 8. Let's sum up to 9. Okay, when I go to sum to 9, same thing. I would be looking through the table. So once you have that table, you can reference that again. That'll help you. I can get a 3 and a 6. I can get a 4 and a 5, 5 and a 4, and a 6 and a 3. These are mirror images, but remember, order matters, right? Because die 1, die 2, or die 2, die 1. Okay, so we want to be able to think about that. So this is a 4. I've got 4 possible outcomes for that. 1, 2, 3, 4. And then sum of 10. I think one of your homework problems is actually enumerating out the whole sample space for a lot of these things here. So that'll give you a chance to think about how all this holds together. So summing up to 10, I can do 4 and 6. I can do 5 and 5. And I can do 6 and 4. Okay. All right, so that gives me 3 possible, right? So now the probability of summing up to 8 is going to give me, I've got 5 out of 36, right? Because 36 total possibilities, 5 outcomes. Probability of summing up to 9 is going to be 4 out of 36. And then the probability of summing up to 10, this is the sum, I'm not writing the whole thing out, but it's summing up to 10, is 3 out of 36. Okay, so now these are my individual probabilities. So if I want to look at the probability of 8 or a 9 or a 10 happening, right, I'm going to add all these things up and I'm going to say, 5 out of 36 plus 4 out of 36 plus 3 out of 36. It's my individual possible outcomes because I don't have any overlap between these three. So I just get 12 out of 36, which is about 0.33 repeating. Okay. All right, so part B says we can get doubles, which means I get 5 and a 5, a 1 and a 1, a 2 and a 2, doubles, or a sum of 7. So let's write out what our sample spaces are. So doubles, you can get 1 and a 1, 2 and a 2, 3 and a 3, 4 and a 4, 5 and a 5, 6 and a 6. Okay, and a sum of 7. Okay, we're going to do the same thing that we did in part A, but just summing up to 7 now. 1 to 6, 2 to 5, 3 to 4, 5 to 2, and 6 to 1. 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5. Did I miss one? 2, 5, 3. Oh, I missed 4, 3. 4, 3. Okay. All right. You're going to make sure you're checking because 3, 4, and 4, 3 both sum up to 7. Okay, so now the probability of doubles, I've got 1, 2, 3, 4, 5, 6, which is 6 out of 36, right? 6 in our event space and 36 possibles in our sample space. Probability summing up to 7 is going to be equal to 1, 2, 3, 4, 5, 6. Also 6 out of 36. Okay. Now the probability of doubles or a sum of 7 is going to equal to probability of doubles plus the probability of 7. I'll just write this in here just so you can see how this is. Probabilities of doubles or a sum to 7. Okay. So the doubles, 6 out of 36, and the 7, 6 out of 36. Let's see, do I have any in my doubles that sum to 7? I do not. Okay. That means my probability of doubles that sum up to 7 is equal to 0. There's no overlap between them. So I'm writing this in here. We didn't write it in the previous examples, but it's here now, which is equal to 1/3. 12 out of 36 is equal to 1/3. Okay. And we're almost done. Bear with me here. Part C says we're going to sum greater than 9 or less than 4. A lot of these, this is a great question here, part C, because it's getting you set up for, we do a lot of these types of problems that are within a range of values, like greater than this, less than that, or within this particular range here. So this is good to kind of think about. So I'm going to write this as the sum is greater than 9 or the sum is less than 4. Okay, so this is, I can even write little mini parentheses in here if I want to. Okay, so I want to look at these possibilities here. So the first thing I'm going to do is my sum is greater than 9. So in my sample space for my my 2 die rolling, I'm going to look through and I'm going to look through for all these places where the sum can be greater than 9. And I'm going to get 4 and 6, 5 and 5, 5 and 6, 6 and 4, 6 and 5, and 6 and 6, right? So I can sum up to 10, I can sum up to 11, and I can sum up to 12, okay? And then my sum less than 4, okay, so that means I'm going to be summing up 1 and 1, 1 and 2, and 2 and 1, right? So sums up to 2, sums up to 3, it sums up to 3, and that's it, okay? So I've got these possibilities here. So now when I put these in, I don't have any overlap between these two either. So when I go to put these in, the probability sum greater than 9 and sum less than 4 is going to equal to these two being added together. So I've got 1, 2, 3, 4, 5, 6 out of 36 possible, plus 1, 2, 3. 3 out of 36 possible, which is 9 out of 36, which is 0.25. You'll often see these types of problems here where we have, given a range of values, especially when we get into equations where we're mapping out probabilities using equations. Okay, so what's least likely to occur, A, B, or C? So I'm looking back through my answers. So my answer for part A was 0.33. My answer for part B was 0.33. And then my answer for C was 0.25. Okay, so then these two are equally likely to occur, A and B, and then C is the least likely to occur. It's got the smallest probability, right? So the smallest probability means it's the least likely to actually happen, okay? So that was it for our example, and that's actually the end of our chapter content for chapter 2.3, okay? So I'm gonna have office hours this afternoon if you guys wanna take a look at the homework for 2.3, if you wanna ask me questions about 2.2, or if you wanna ask me questions about the lecture from today or yesterday, okay? Anybody have a quick question before I end the meeting? If you guys are all set, you don't have any questions, you're free to take off.
Actually, I was wondering if on the homeworks and quizzes we would be allowed to do like A with a line over it to show the complement of it, because like that's what I'm used to, and I feel like it'll just help me like know what I'm doing if I keep doing that.
That's fine. It's totally fine. Our book uses A with a C, and
Yep.
so other books that I've looked at and other things use A with the bar. I'm okay with it. I can't think. I don't think we're not doing any vector stuff, so I think it should be fine. Like that was like the time when like the line might actually get confusing, if you're using that. And it's kind of just a notation, so I'm okay with that if you want.
Okay,
That's
awesome.
fine.
Thank you very much.
Yep. Any questions you want to ask? Otherwise, great day.